All right, welcome back with second installment of Nuclear Chem. In this little segment, we're going to show you what it means to be a particle first, because that's a significant chunk of our homework. Knowing the difference between the particles, knowing who has a heavier mass, who has a lighter mass, who's more dangerous, those kinds of things, who can penetrate through tissue easier. And many of these particles we've seen earlier, we just haven't written them specifically in this way, but a lot of these numbers should make sense. So for example, our first particle here is protons and neutrons. Because this is nuclear chemistry, this would be our major focus for this chapter. Notice that protons and neutrons have the same mass number of 1. And we'd expect that based on what we learned in our chapter before, at least 2 weeks ago when we covered the subatomic particles themselves. This bottom number is the atomic number. The atomic number represents the number of protons. So again, notice we have one proton is a proton. We have no protons and a neutron. So in a way, you can think of that as their nuclear charge in a sense. Protons have a positive 1 kind of charge, so they have a 1. Neutrons have a neutral charge, so they have a 0. So typically we would write charge in that upper right corner, and that's for most chapters in chemistry that deal with valence electrons. However, in this chapter, you can kind of sense that that's an easier way to understand that bottom number is the charge of the particle in the sense of its nuclear charge. So these particles aren't anything new. These are ones we've covered before. One thing that we haven't covered is a positron. That's a new one for this chapter, and it's really specific to this chapter only. So after this chapter, you can almost forget it forever until the final exam. A positron, though, is an electron with a positive charge. It's kind of a made-up particle in the sense that scientists recognized a phenomenon that looked like an electron but was positive, so they just called it a positive electron, or positron in this case. Because it takes over 1,800 electrons in order to make the mass of a proton or neutron, notice their mass is 0. So for both of these particles, they're lightweight. That just means they're going to be more dangerous. The bigger you are, the slower you move, and you're easier to stop. The faster you are, like a sports car, you're going to go super fast. You're going to, be a lot harder to catch, a lot harder to stop. And that's what we see with mass. These mass numbers, when they're smaller, they're more dangerous to the human body. They can penetrate deeper. Doesn't mean that either one of them does damage. They all do damage. But if you're lighter, in the sense of having a 0 mass number, you are a smaller particle than, say, at least smaller in mass than protons and neutrons. So in a way, a positron is the charge of a proton because it's got a positive 1 down here, but it doesn't have a massive 1, so it's not a full-blown proton. It's just the charge of a proton, and we'll see why it's important to understand the creation and the invention of a positron as we look at some of their reactions. So again, this one's the new one, so commit it to memory, because electrons really haven't changed. They have no nuclear charge, but they are opposite of a proton, so I do give them that -1 atomic number to kind of give you an idea that it really is charge that we're thinking about, even though we're not writing it in that upper right corner in this particular chapter. So as we look at examples, we want to make sure that we can recognize the direction, the process of how atoms can become more stable. So this first type of nuclear change, this nuclear decay, is called beta. So there is alpha, beta, and gamma that you probably have heard of. We mentioned alpha decay before with the gold foil experiment. We'll see it coming up. But notice in this situation with beta decay, what happens is a neutron becomes a proton. So notice this neutron here became a proton over here. So if you're a neutron becoming a proton, that's unique because that's going to move you forward in the periodic table. So if you're some element in the periodic table, you're going to have some number up top, you're going to have some symbol, and this is really just moving you over one box in the periodic table. And you'll see that coming up with an example. The example they're showing here is the carbon-14 atom becoming the nitrogen-14 atom. So again, we're changing the element because we're changing its nucleus. We're changing that marble inside of that Bush Stadium kind of concept. So what's really happening here? Well, imagine if a neutron really is just, so if a neutron is written as 1 over 0n, if we were to think of that as a particle, maybe what a neutron really is, if we were to zoom in really close, and again, this is a cartoon understanding of what it is, or at least what you can imagine it to be, maybe it's just a proton mixed together with an electron. If that's the case, look at the math. A 1 on top for a proton and a 0 on top for an electron gives you 1 in mass. A 1 on the bottom for the atomic number, the charge, so to speak, for a proton, and you have a -1 for that of the electron. 1 minus 1 gives you 0. So mathematically, it makes sense. We're just saying if there's too much cushion in this atom to be stable, then we can just take the electron from our neutron from inside and just eject it, kick it out. So no longer is it inside. What's left over is essentially just a proton, and that's what we see. So is that what really happens? Probably not. But it does make sense of the math, and it does show us that eventually all we're really doing, again, is moving forward in this process of the periodic table. So the easiest way to understand beta is move forward, because there's other ways to move backwards. And this is the only one of the 5 that we teach you that's going to move forward. So as we understand beta emission, this beta particle is a synonym or the same as an electron. So beta and electron are the exact same thing. It's just their name in nuclear chemistry versus their name in normal chemistry, so to speak. So they can be used interchangeably. And what's unique about this electron here is it came from the nucleus. And never have we said that's possible until now. So magically, electrons are just squirting out of the nucleus from radioactive atoms, and scientists can register those on, their Geiger devices and so forth, their radiation devices. So this is just one type of radiation that we can see from the nucleus, and it's the only one that can move us to the right in the periodic table. The most common example of this is carbon-14. Carbon-14 is the radioisotope that we said you can age, dead organisms frozen in the ice, because their carbon-14 disappears where their carbon-12 and 13 remain intact. So based on how much is missing, we can show you in the applications of this chapter in a separate video that you can kind of backdate using half-life of how old or how long they've been, frozen in time, so to speak. As we look at definitions for this chapter, we want to make sure that you can understand that parents do come before their children. So here we have this carbon-14 parent, and that's producing this nitrogen-14 daughter. So be aware that when they're asking for parents, they're asking for reactants. And when they're asking for daughters, they're asking for products and reactions. You'll see some of those in the multiple choice in particular. Even though nuclear chemistry sounds scary, sounds intimidating, sounds like you need to be Albert Einstein to figure it out, it's really not that bad. Because if you look at this slide, it's really just addition, subtraction on top with the mass numbers and on bottom with the atomic numbers or the charges, so to speak. So you can imagine that if you start with 14, you should end with 14. So in a way, it's like the law of conservation of mass. If you start with a mass of 14, then all the pieces that you produce in the product should also equal 14. And for at least 3 of the examples that we show you, this is the case. And with gamma radiation, it's also the case because it's just 0. So really 4 out of the 5 are going to be the same number on top, the same mass number on top. Here's the tricky part though. If you start at 6 and you go to 7, you're producing that -1. So remember, 7 plus a -1 is the same thing as 7 subtract 1. So students hate this math down here. At least the ones that don't like math tend not to like this kind of process down here. But remember, beta is a way to move forward in the periodic table. So when you're moving from carbon's little space in the periodic table, number 6, really beta is just moving forward to nitrogen number 7. So if you don't like the math, think of the direction, and the direction here is forward. So let's try an example. We have lead-214 as a parent. If we look at the periodic table, the number is 82 for atomic number. And then it produces a beta particle. So in this case, who's the daughter? So it's kind of the reverse of the Jerry Springer kind of concept on, who's the daddy. In this case, it's, who's the daughter. And we can recognize this probably by just looking at the periodic table and moving forward. But mathematically, let's think about it, because that's what you'll have to do on the exam. Although on the exam, you could look at the periodic table and move forward as well. So if we have a 214 lead, and we produce a beta particle or an electron, because they're really the same thing. Notice this is an emission because it's like coming out of the tailpipe of your car. It's escaping the nuclear reaction, so it's just like escaping the tailpipe of your car. If we have 214 on top, we should maintain 214 on top, because 214 equals 214 plus 0. Then down here, this is where students tend to get it backwards. If you think 82, you're adding a -1. And as soon as students think add, they're thinking, oh, maybe that's 80, maybe that's 83, maybe that's 80, 81. How do we know the difference there? Well, if you take 81 minus 1, that would give you back to 80, and that's the wrong direction. If you take 83 and then you subtract 1, you're going to get back to 82. So when we look at 83 on the periodic table, and we see that that's just bismuth. So when you find out who's 83, and we're not talking about, say, your grandma or your grandpa, we need to look at the periodic table, and we can really just cheat off of those and recognize straight from the periodic table that if we don't like math, could we just look forward? And let's show you that that is possible. So if we show you that, here's our periodic table from the exam. Notice with our lead, so here's lead down here. And notice all we did was we moved forward 1. And that's exactly what we would say would happen in a beta emission. You're always moving forward in beta 1 box in the periodic table. So let's try another one. Let's try positron emission. So in positron emission, what we have is a little bit different, because this one's going to move left instead of right. So you're no longer moving forward, you're going to be moving backwards towards that band of stability that we showed you in a previous video. So what's going on here? Well, again, very similar but different. The nucleus is changing, but notice this proton is now becoming a neutron. So how can that magically happen is what we're after. Well, again, a proton, if we think about it, is 1/1p. In a cartoon kind of analogy, if protons are 1/1p, and that's really what this particle here is, how does it become a neutron? Well, a neutron is 1/0. So in order to become 1/0, protons have to lose that atomic number 1. And what is that? Well, scientists didn't really know. And anytime scientists don't know anything, they just make it up. And in this case, they make up that it does have no mass, it has a positive charge, and it's the size of an electron. So this is where they came up with the idea that we need something new that hasn't been discovered yet, so let's just name it based on things we do know. It's positive, it's an electron in size, so let's just call it a positron. And that's really what's happening here, is protons are just losing their positivity in the form of a particle that scientists can read from various devices. So just another type of radiation. So here with potassium, we see that potassium-40 is radioactive. So that tells us that anything containing potassium in our bodies or in bananas is also radioactive. This is a very rare isotope, so it's not a huge amount, but if you were to put a banana underneath a Geiger counter, some radiation would be forming specifically from the potassium-40 among the carbon-14 and other things that are in there too. But notice the math isn't a whole lot different. 40 still equals 40 before and after the arrow, so the top numbers still add up to 40 on both sides. And then both sides also add up to 19. It's just that this one's a little bit easier because 18 plus 1 is 19. You don't have to worry about negative numbers, and you don't have to worry about messing things up and going backwards. But again, it's a little bit easier just to think, if positron emission is moving to the left, why not just remember it that way? If you don't like the math, just avoid the math and say that if you're going from potassium, number 19 on the periodic table, really you're just going backwards a box in the periodic table to argon 18. It's not as easy to see that in the periodic table because you're going to go back up a period in the periodic table because noble gases are always on the right. But even if we were to show you that, you could see that it's still the same kind of concept. We just have to make sure that you can realize what's happening here is if you're potassium over here on the left, you're really just going backwards, and that takes you to argon number 18. So this is a way of moving left in the periodic table instead of right, as we saw with beta emission. A similar but different way of doing positron emission is electron capture. These two actually accomplish the same thing. And in a way, this is the exact reverse of beta emission. So in this situation, we have a proton, and an electron gets sucked in to the proton. So now it starts to really seem like that cartoon episode that we had a moment ago could actually be true. So if we have what looks like a proton, and then this electron, this 0 over -1e gets sucked inside, we said, why couldn't that happen 2 weeks ago when we said all this negative was outside of this positive one? They just combine because they're like two opposite magnets that attract, and it turns out can. So what does this equal? Well, it equals something that has both a proton and now an electron kind of glued together, fused together. And if you do the math, 1 plus 0 on top is still just 1, and 1 minus 1 on bottom is just 0, and that's really just a neutron. And that's what we see here as what's forming. So it looks like that cartoon was pretty accurate in the sense of what seems to be happening. It's probably a whole lot fancier than what we're actually seeing, but at least in a cartoon kind of model, it makes sense of the math that is observed. What we see here with mercury is that Gabriel would have been very happy to know that you can turn mercury into gold. It just takes a very long time. Its half-life was probably a whole lot longer than he was willing to wait in order to see it, and it's also a very rare isotope, so the concentration of mercury turned into gold is really small. But in the grand scheme of things, the math is still almost identical to what we've seen in the past. 197 stays 197. Now you do have a negative number, so 80 subtract 1 gives you 79. But really this is just a way of going left separately from what we saw a moment ago. So let's show you that real quick. So if you have mercury, you're over here. So mercury sits here in the periodic table. And notice we're just moving left to gold. So this can be done through positron emission, or it can be done through electron capture. So far we have 3 ways of travel. We can move forward with beta. That's when you kick out electrons. And we can move backwards with electron capture, and then also with positron emission. So a way to make your life easier is just think of the directions. Don't worry about the math. And you can save yourself a lot of time on the calculator and on the test. So here's an example. We have fluorine isotope 17. So fluorine 17, and it undergoes positron emission. So let's try to write that out. Give ourselves a little practice writing it out. So we have fluorine 17 undergoes positron emission. So if we have fluorine 17, it is number 9 on the periodic table. If it undergoes positron emission, we have emission always on the right, so that's 0, positive 1, E. So then do the math. Well, the easy part of the math is 17 equals 17 plus 0. And then it's a matter of, over here, do we choose 8 or 9? Because those are going to be the obvious choices on multiple choice to think about. So is it 10 plus 1 that equals 9, or is it 8 plus 1 equals 9? So who's 8 other than maybe your kid brother? Look at the periodic table and you'll find 8 is oxygen. So when we do an example like this, what we're trying to show you is that even if you can't do the math, because a lot of students don't like math, and I admittedly don't like it either, you can just look at the periodic table. So if we go back to the periodic table one more time and show you, if you're at fluorine and you're doing positron emission, so here's fluorine up in this corner with the halogens, we can expect that if we're going to the right, that's going to be beta. If we're going to the left, that's going to be either positron emission or it's going to be electron capture. And those are our choices. So even if you don't like the math, just based on the position of the periodic table, you can guess these answers relatively quickly and survive just fine. So one of the last major types we're going to talk about is alpha decay. Alpha decay is the only one that the mass number changes. Alpha was also used in the gold foil experiment to actually find the nucleus. Go figure, it's actually coming from the nucleus of another atom to discover the nucleus of all atoms. So the irony there is pretty interesting. But we do call this a helium isotope in a sense because it is just the 4,2 helium that we'd expect on the periodic table. But because this comes from the nucleus, it has no electrons. And if it has no electrons, it technically is a +2 cation of helium. We don't deal with charge in this upper corner because we don't want you to confuse it with the math that we're doing separately. So even though this is technically a +2, we never really talk about it other than we mentioned it with the gold foil experiment. We don't want you to think of this +2 in any sense in this chapter because we don't want you to throw it in with the mass numbers and start doing addition, subtraction that's going to give you wrong answers. So it is a +2 kind of radiation, but just for now, think of the mass numbers and the atomic numbers because that's where nuclear chemistry is going to focus on. So alpha emission is a big chunk. It's kind of like saying if you go to the doctor says if you don't lose a bunch of weight in the next 15 seconds, you're going to die. So this nucleus is basically dying, and it needs to lose weight fast. So what you're seeing here is you're losing because you're gigantic. Your atomic number is bigger than 83. So you're really past bismuth on the periodic table. And most of these have atomic weights that are radioactive, and that's visible by the parentheses that you see around their atomic weights. So how do you lose a bunch of weight in 15 seconds? Well, you just take a big knife and you chop off a chunk. And notice when we chop off a chunk, it just happens to be the size of a helium atom, or in this case, a helium nucleus. But there are, this is just the marble in the center. There is no electrons in its stadium, and that's why it's a +2 kind of, chunk. So in its a way, like you could think of it as being like leprosy. You're losing your noses, your elbows, your ears to this radioactive decay process, and all those pieces just happen to be of one particular size, and that's what we call an alpha particle, which looks like a swimming fish, so to speak, in the Greek alphabet. So here's a really big one, uranium. Uranium-238 decays into uranium-234. So notice this is the first and only time that the top number changes. So when the top number changes in the daughter, you know it has to be alpha because that's the only time the top number changes in introchem ever. And the reason it changes is because you lost 4 in that nucleus. You also lost 2 protons, so notice 90 is your daughter when you were started out as 92. So you lost 2 on the bottom, you lost 4 on the top, and that's the only time we're going to move left twice, and it's the only time that the top number is going to change, which is probably the easiest way to recognize it in the periodic table. So let's look at uranium real quick on the periodic table and just prove to you this directional kind of method is probably a little bit easier than anything else to understand. So if you're at uranium here, notice if we go forward, that's going to be beta. If we go backwards, that's going to be positron or electron capture. But if we go backwards 2, that's alpha. And that's the answer, thorium, that we were expecting. So again, beta forward, positron or electron capture is left, but now we know that left 2 is alpha. And that's really a summary of everything that we see in this chapter. So here's a prettier version of that from what I just showed you, but this is the picture that we see in our labs. This is a picture we see in our books and now in our notes. It's really just a matter of beta moves forward, positron and electron capture accompany the same thing, all of which the mass doesn't change. But then we have alpha emission that goes back too. So if you memorize this chart, you're going to be pretty good for most of what we see on the exam. If you memorize the bottom in the sense of who has a certain mass, who has a certain charge, at least of the nucleus of that atomic number at the bottom, you can get through most of the rest of the questions concerning particles. So this is a great summary slide for everything that we've seen in this chapter so far that makes it to the exam. The reality of this is it's not so simple. We show you one step on, in these examples in class. In reality, to swim to shore for radioactive uranium, it takes, 10 or 12 steps. So there's lots of alphas, lots of betas that are simultaneously happening in order to become non-radioactive. So we only show you one-step kind of processes in class and in the homeworks and exams. But the reality is it takes many steps in order to get to something that's non-radioactive. One unique piece of information about uranium is there's a very large uranium deposit in Bismarck. It's not been used probably since the Cold War, but over many steps, it becomes lead. So you can imagine, with all the towns named after lead in this area, it's very likely that a lot of that lead, millions and billions of years ago, was probably uranium at one point. Makes for a good story anyway. The last one is gamma radiation. And this video is getting a little long. It's not really what I wanted, but I wanted to keep all these together so that you can see their differences in the same video. This is the last type of nuclear change, the last type of nuclear decay processes, and it doesn't change the math at all. You can imagine this analogy of just chopping chunks off of your body. If somebody were to chop a leg off of you to lose weight immediately, you would scream. And what we're seeing with gamma rays and gamma radiation is anytime you chop off a chunk called helium, which we call an alpha particle, what also tends to happen is you produce a gamma ray. Gamma rays are 0/0 with a little diving fish symbol in the Greek alphabet, and they're not changing the math whatsoever. Because they have no mass and no atomic number, they are the hardest to stop, but they're the lightest particle, the most dangerous particle of the bunch. The only thing that's more dangerous than that was the cosmic ray. We talked about it in our last chapter. So there's really no math to understand here. There is really no forwards or backwards to understand here. It's just when alpha emission tends to happen, gamma rays are also produced. And that's that mass to energy kind of concept. So in a separate video, we're going to show you the applications of nuclear chemistry. So we'll catch you then.